Welcome to FSA Pod, where we take a stack of complex information and really try to pull out the nuggets you need to know. I'm your host.
And I'm your expert guide.
Today, we're diving deep into, well, a really critical piece of the commercial spaceflight puzzle.
That's right. We're looking at FAA Advisory Circular AC 450.1151A.
Which is all about high-fidelity flight safety analysis for launch and reentry vehicles. Sounds complex.
It can be, but think of this deep dive as your shortcut, a way to grasp how the FAA ensures public safety, especially now that space operations are getting more common.
So whether you're an engineer working on this stuff or just someone fascinated by rockets.
Exactly. We're here to unpack the essentials from these guidelines. Our goal is really to give you a clear picture of what's important in this AC.
And this AC, it lays out one way to meet the FAA rules for flight safety, right? For 14 CFR Section 450.115.
Precisely. It's an accepted method for launch and reentry safety analysis.
Okay, let's get straight into it then. It's a method, but you said it's not the only way.
That's a key point. Well, this AC provides a very detailed approach. It's not the single path to compliance.
So operators have other options.
Yes, the FAA administrator can approve other methods. The main thing is they have to show an equivalent level of safety.
Makes sense.
So this AC, it's advisory. It's meant to clarify the existing regulations, give a clear pathway for operators. It's not creating new rules out of thin air.
And it's useful for everyone involved, companies, FAA evaluators.
Absolutely. Applicants seeking licenses, operators modifying existing ones, and yeah, the FAA personnel reviewing the applications.
So when does a company actually need to perform this, high fidelity level of analysis?
That's a really fundamental question. This specific AC, it focuses mostly on the how.
Right.
The guidance on when you need it is actually in a different AC. That's 450.113-1. But generally speaking, you need this high-fidelity approach when the potential risks to the public are, let's say, significant enough to warrant a really detailed, precise look.
Higher stakes, deeper analysis.
You got it. If the potential consequences are bigger, you need a more rigorous examination. And this AC provides that framework.
Right. So the big picture, the main goal is always public safety. What's the absolute core requirement these analyses have to meet?
The core requirement, and this comes from Section 450.11AA, is that the operator's analysis method has to account for all reasonably foreseeable events and failures.
All of them.
Yes, any failure of a safety-critical system during nominal flight or, importantly, during non-nominal flight, basically anything that could potentially jeopardize public safety.
So it can't just be a quick check?
No, definitely not. It needs to be comprehensive, systematic, a thorough evaluation of what could go wrong.
And when they say comprehensive, what does the analysis actually need to show? What must it demonstrate?
Okay, so Section 450.115B1 says the analysis must prove that any public risk meets the safety criteria laid out in Section 450.101.
The main safety rules.
Exactly. And this includes considering any mitigations they're putting in place, steps to reduce the risk.
And the uncertainty. Things they can't know for sure.
Crucially, yes. It has to account for all known sources of uncertainty, and it has to use methods the FAA accepts for doing that. It's about showing, with confidence, that the risks are acceptable.
And it's not just about the overall risk level being okay, is it? Do they need to pinpoint the biggest problem areas?
That's right. Section 450.115B2 makes that clear. The analysis has to identify the dominant source for each type of public risk.
Dominant source, meaning?
Meaning the biggest contributor. So for toxic hazards, for inert debris, for explosive debris, whatever the hazard is, they need to figure out what's the primary driver.
Like what phase of flight it's most likely?
Exactly. Flight phase, the specific hazard source, and the specific failure mode that kicks it off.
That level of detail seems really important for fixing things.
It allows for very targeted mitigations. You focus your efforts where they'll make the most difference.
Okay, so that's the what and why. How do you actually do one of these high-fidelity analyses? What are the main steps?
Well, the AC breaks it down into key stages.
Yep.
It all kicks off with mission definition and hazard identification. That's Section 7.
Makes sense. Start with mission.
Absolutely. You need an incredibly clear, detailed picture of the entire mission first.
What kind of details are we talking about? Just the launch time?
Oh, much more than that. The mission objectives, a full description of the vehicle itself, launch or reentry.
The flight path.
The planned flight profile, yes. But also any potential variations from that path. And really importantly, identifying all the places, the locations that could be affected.
You can't assess risk without knowing what you're doing and where.
Precisely. You need that baseline. Know the plan, know the area.
And then comes the maybe less fun part, thinking about everything that could go wrong, hazard identification.
Exactly. That's where you identify all the functional failures tied to reasonably foreseeable hazardous events. That's Section 450.107B.
Can you give an example?
Sure. Things like a stage separating inadvertently at the wrong time, or maybe an engine failing to ignite when it's supposed to.
Things that could definitely cause problems.
Right. The AC emphasizes looking at all credible scenarios, both during normal flight and if something malfunctions.
So you make this big list of potential problems, then what? Just cross your fingers.
No, definitely not. The next crucial step is hazard management, developing specific strategies to minimize that public risk.
Like what?
Well, the AC gives examples. Maybe adjusting the timing of when you jettison used stages, or setting really clear boundaries for how far off course a vehicle can stray before, the flight's terminated.
That termination system's right.
Yes. Or even delaying a launch if the weather's bad, like high winds that could widen the potential danger zone.
So it's proactive, planning ahead to avoid trouble.
Exactly. It's all about trying to prevent bad outcomes before they happen.
Does this also include things meant to fall off, like spent boosters?
Yes, absolutely. That stage also requires carefully considering any planned jettison hazardous debris, like those discarded stages or fairing pieces, especially for suborbital flights. That's covered in Section 450.109B.
Need to know where that stuff might land, too.
Precisely. Analyze where it might fall and any risks it could pose.
Okay, so you thought about what could go wrong, how to prevent it, but if something does break apart, you need to understand the pieces. That brings us to hazardous debris characterization, Section 8.
That's the next big piece, a really critical part required by Section 450.121A is to thoroughly characterize the hazardous debris.
From both normal events and malfunctions.
Yes, normal things like planned jettisons or even an on-trajectory breakup, and then also debris from malfunctions, like a vehicle breaking up off course or hitting the ground intact.
And how the debris changes over time.
Right. The characterization needs to be a function of the flight sequence, because how a vehicle breaks up might be different at different altitudes or speeds.
What factors go into predicting what kind of fragments you might get from an unexpected breakup?
Section 450.121B points to the key things. First, all the foreseeable causes of a breakup or intact impact.
Like aerodynamic stress.
That's one. Second, the vehicle's structure, how it's built, what materials are used, and third, any energetic effects explosions, basically.
Predicting exactly how a rocket breaks up seems incredibly difficult.
It is. It's hugely complex. And the AC acknowledges that predicting fragmentation is inherently uncertain.
So how do they handle that uncertainty?
Often they take a conservative approach. They develop comprehensive debris lists based on the possibilities, rather than trying to nail every single fragment perfectly.
Using past data.
Very much so. They rely heavily on empirical data from tests, from previous mishaps to make sure their models are consistent with, or more conservative than, what's actually been observed. That's in Section 450.101G.
That reliance on past events is interesting, learning from history because the physics is so complex.
Exactly. In the face of this complexity, you learn from experience and you err on the side of caution. That's fundamental for public safety.
What specific info about the vehicle itself is needed for this characterization?
Quite a bit. Detailed physical properties, mass, dimensions, materials of the vehicle, and major parts.
Trajectory data, too.
Yes, detailed trajectory data for nominal and malfunction scenarios. Timing of key events like engine burns, stage separations.
What about the flight termination system?
The rules for activating the FSS, yes. And also a deep understanding of material strengths, design limits, any known weak points where it might fail under stress.
You mentioned different kinds of breakup earlier.
Right, the AC lists several types. Catastrophic explosions, obviously.
Yeah.
Structural breakups, which could happen on or off trajectory due to aerodynamic forces or other issues.
Re-entry breakup.
Yes, from aerothermal heating. And also intact impact, where a large piece hits the ground and maybe breaks up further or explodes then.
And the materials, like composites versus metal, must make a big difference.
Absolutely. Composites fracture very differently from metals. They have different densities, strengths, melting points. All that affects the debris.
And onboard energy sources, fuel, compressed gas.
Those can dramatically change things. Explosions from propellant, rapid gas releases, they significantly influence the breakup and the resulting debris field.
Okay, one thing that really jumped out was about small debris being hazardous to aircraft, even tiny pieces.
Yes, that's a critical point. Even fragments as small as zero point 0.4 grams, less than a paperclip's weight,
Mm.
can be incredibly dangerous to aircraft.
Why is that? Seems counterintuitive.
It's all about the closing speeds. An aircraft flying hundreds of miles per hour hitting even a tiny, fast-moving object.
Mm.
The impact energy is huge.
Enough to cause serious damage.
Easily. Damage engines, puncture the fuselage causing decompression, rupture fuel lines. Any of those could be catastrophic. It's quite sobering.
It really is. Okay, so now we have this list of potential debris. We understand its basic nature. Next, you need to figure out how it flies through the air. That's aerodynamic and harmful debris characteristics in Section 9.
Precisely. To predict where it might land and how hard it might hit, you need its aerodynamic properties. This is where ballistic coefficients become really important.
Ballistic coefficient, that's basically how easily it cuts through the air.
Kind of, yeah. It's a measure of how well it overcomes air resistance. It combines the fragment's mass, its cross-sectional area, and its drag shape.
So higher ballistic coefficient means it travels further.
Generally, yes. It's less affected by drag.
And I saw something about different atmospheric flow regimes. What's that about?
Right, the air itself behaves differently depending on altitude. Down low, it's continuum flow, acting like a fluid. Way up high, in thin air, it's free molecular flow.
Molecules are far apart.
Exactly, they hit the debris individually, and there's a transitional regime in between.
Why does this matter for debris?
What's interesting is if you use a simple ballistic coefficient calculated for low-altitude continuum flow up in the free molecular region, you can actually underestimate the drag.
Which means you might predict it travels further than it really does.
Or, more critically for smaller pieces maybe, that it doesn't slow down as much as it should. This is especially relevant for those small bits hazardous to aircraft. The analysis has to account for these changing air dynamics.
So the air density and behavior changes. What about the shape of the debris?
Hugely important. The drag coefficient, a key part of the ballistic coefficient, depends heavily on shape. Streamlined versus blunt makes a big difference.
Does the AC help with that?
It does. It provides tables with estimated drag coefficients for common tumbling shapes. Spheres, cylinders, plates, boxes at different speeds, different Mach numbers.
So if you don't have test data, you can estimate.
You can approximate the shape and use these tables to get a reasonable drag estimate, yes.
What about lift? Falling debris doesn't usually generate lift, does it?
Not sustained lift like a wing. But the AC mentions lift uncertainty. As fragments tumble, their orientation changes, so any momentary lift forces vary randomly in direction.
So it adds another layer of unpredictability.
Exactly. It's often represented statistically, maybe as a ratio of lift to drag uncertainty. Flatter shapes might have more potential for lift variations than spheres, for example.
The AC also mentions creating a hazardous debris model. What goes into that?
According to the regulations, Section 450.121D5, this model needs to be a comprehensive description. Physical characteristics, size, mass, aerodynamic properties, potential harmful characteristics
For all the debris.
for all identified hazardous debris. And the model needs to work for any point in the flight, for any trajectory. It should generate a representative set of debris for a given breakup scenario.
Different models for different breakups.
Often, yes. Different lists for different phases or failure types, because the fragments will vary. The model needs to adapt to changing vehicle state and atmospheric conditions.
And I think you mentioned grouping debris to simplify things.
Yes, the idea of hazardous debris groups. You categorize fragments with similar aerodynamic properties, similar average ballistic coefficient, similar drag and lift behavior over different speeds.
Makes the math more manageable.
Much more manageable when you're potentially tracking thousands of fragments.
What about re-entry heating?
Right, for high-speed reentry or late ascent failures. The model also needs aerothermal heating properties. Material type, shape, to see if things might melt or burn up completely.
Section 9 also mentioned other energetic and hazardous debris. What fits there?
It's kind of a catch-all. Things that could still be dangerous after impact, like batteries holding charge.
Leftover propellant?
Intact tanks with propellant or pressurized gas, yes. Could rupture or explode? Any ordnance. Compressed springs releasing energy. Even just really hot hardware causing burns or fires.
So you need to evaluate those residual energy sources, too.
Definitely, under normal conditions and malfunction scenarios.
Okay. Debris identified, aerodynamics understood. Now, where does it actually go? That's propagation of hazardous debris to impact, Section 10.
Exactly. The main goal here is calculating the impact probability distribution for each debris class, specifically at locations where people might be. That's section 450.135b.
How do they do that? Simulation.
Yes, simulating the trajectory of each representative piece from breakup or jettison until it hits the ground or is no longer a hazard.
What data fuels these simulations?
Detailed atmospheric data is crucial. Air density, wind speed, and direction at all relevant altitudes. Speed of sound.
How accurate does that need to be?
Very. They use sophisticated atmospheric models for density. And for winds, which are critical, the AC recommends official forecasts from sources like the Department of Defense or NOAA.
But wind forecasts aren't perfect. There's always uncertainty, right? How do they handle that? It seems impossible to predict the exact spot.
You're absolutely right. Uncertainty is inherent. They use things like self-breakup state vectors to define the initial debris conditions, considering forces at the moment of failure.
And for the uncertainty.
They typically use statistical trajectory sets, run lots and lots of simulations, varying the starting conditions and the external forces slightly each time.
To get a range of possibilities.
Exactly. To map out a probability distribution of impact points. They specifically model wind uncertainty, how the actual wind might differ from the forecast, and that lift uncertainty we talked about.
Creating a sort of probability cloud for each debris type. How are the actual trajectory calculations done? What physics?
They use ballistic trajectory generation, physics-based models solving equations of motion.
Accounting for space and atmosphere?
Yes. Vacuum propagation high up and atmospheric effects lower down. Things like gravity, including Earth's oblateness.
It's not a perfect sphere, right?
Right. Plus air resistance, drag,
Yeah.
and even Coriolis and centrifugal forces from Earth's rotation.
What if a motor keeps firing after breakup?
That requires more complex calculations, 5 or 6 degree of freedom, DOF models that track orientation and thrust. Same if a piece generates consistent aerodynamic lift that also needs 6 DOF.
And you mentioned debris burning up. Demise?
Yes, hazardous debris demise or ablation. High-speed atmospheric entry can cause fragments to melt or vaporize. That obviously changes the trajectory and reduces ground risk.
Okay, so after running countless simulations, you have a massive amount of potential impact points. How does that become an impact probability distribution? That's section 11.
The AC says you can represent this distribution in a few ways.
Right.
One is using functional distributions, mathematical functions like Gaussian curves or skewed distributions.
Like a statistical summary.
Kind of. They describe the spread, the average landing spot, how clustered or spread out the impacts are.
What's the other way?
Using histogram distributions. You overlay a grid on the ground area and simply count how many simulated trajectories land in each grid cell.
Giving a direct probability for each little square on the map.
It's essentially, yes,
Yeah.
a probability of impact for each specific ground area.
Right. So now you know where debris might land and how likely. The next logical step is figuring out how bad that would be. Consequence modeling, section 12.
Exactly. This part focuses on evaluating the potential harm from the different types of debris: inert, explosive, toxic.
Let's start with inert debris, just falling metal, basically. How do they model the consequences?
For unsheltered people, it often comes down to kinetic energy thresholds. How much energy does the fragment have on impact and over what area? They have guidance, injury probability curves based on fragment weight, speed, and the body part hit.
Sounds pretty grim. What about people inside buildings?
For sheltered people, the key is roof penetration. Can the fragment get through the roof?
Depends on the fragment and the roof, I guess.
Precisely. Fragment weight, area, impact angle, speed, and the roof construction type. The AC references standard roof classes and provides effective casualty areas based on the debris characteristics.
What about ships or planes?
For waterborne vessels, they look at direct strikes, deck or hull penetration, even the chance of igniting onboard fuel. Damage thresholds depend on the vessel size. For aircraft, they use complex models called probabilistic aircraft vulnerability models, PAVMs.
PAVMs?
Yeah, they help assess the likelihood that different fragments will cause critical damage based on mass and impact location.
Now, what about explosive hazardous debris? That seems like a different ballgame.
It is. The main hazards there are blast wave over pressure, the shock wave, and impulse, which relates to the pressure's duration.
How do they model that?
The AC provides curves showing how overpressure and impulse decrease with distance from the explosion, based on the explosive yield.
Different models for different propellants?
Yes, models for liquid and solid propellants, considering if it explodes on the ground or in the air, fragment size, etc.
What about buildings near an explosion.
They model structural damage from the blast, risk to people inside from collapse or flying debris, and also the risk of fires started by burning propellant fragments.
And briefly, toxic emitters.
The AC points to another document, AC 450.139-1, for the deep details on toxics. But the basic idea is modeling how toxic clouds disperse and assessing exposure risks based on concentration and duration.
Especially relevant if a vehicle hits intact and then leaks.
Yes, secondary breakup releasing toxic propellants is a key scenario there.
Okay, probability of impact, potential consequences. Now you put it all together for risk assessment, section 13. How is risk defined here?
In this context, risk combines two things: the probability of a hazardous event happening and the severity of its consequences if it does.
How is it usually expressed?
Often as expected casualties, or EC. It's basically the statistically average number of injuries or fatalities expected from one mission, considering all hazards and probabilities.
How do they calculate EC?
By combining the probability of impact for each debris type on different populated areas with the potential consequences of that impact, like the probability of casualty if hit.
Do they look at individual risk too?
Yes. Individual risk, the chance a specific person is harmed. Also conditional casualty expectation for specific failure types, and aggregate risk, the total collective risk.
And they have to report these risk numbers?
Yes. The analysis submitted to the FAA needs to include key risk metrics, like maximum individual risk for population centers and the EC for different failure modes.
All this detailed analysis then informs the flight hazard area, section 14. What is that exactly?
A flight hazard area is a defined region, land, sea, or airspace, that needs controlling or evacuating before a launch or re-entry.
To keep people out of danger.
Exactly. To ensure those public safety criteria are met. These areas can have altitude limits too, creating hazard volumes.
What determines the boundary?
Potential hazard sources, where planned debris might fall, where malfunction debris could land from explosions, breakups, even the potential range of the flight safety system if it's activated.
And these areas are communicated to the public, like notices for boats.
Absolutely. Based on the risk assessment, they issue notices to mariners, not mayors, for water areas and define land hazard areas, LHAs.
To survey, control access, or evacuate.
Yes, whatever's necessary to keep people safe. The boundaries are often tied to specific individual risk thresholds set by the FAA.
Finally, Section 15 wraps up with satisfying applicant submission requirements. What data do companies actually have to hand over?
It's a lot. They need to submit comprehensive data from their analysis, detailed nominal and failure trajectories, state vectors, positions, velocities.
The debris lists.
It's complete breakup and jettisoned hazardous debris lists, physical properties, aerodynamic coefficients, materials, everything.
Failure probabilities, hazard areas.
Estimates of failure probabilities for critical systems, yes. The defined flight hazard areas. Data on debris propagation and impact distributions. Identification of potentially affected people and critical infrastructure. And of course, the full consequence and risk assessment results.
Wow. It really is an exhaustive process.
It is. It's incredibly thorough and data intensive.
That's a truly comprehensive look at what goes into ensuring public safety for these flights. It's clearly much more complex and rigorous than I think most people realize.
It certainly is. This deep dive into AC 450.1151A really paints a picture of the meticulous work involved, from mission planning and hazard ID all the way through detailed risk calculations and setting up those hazard zones.
It definitely shows the commitment to safety in the commercial space world. And for anyone listening who wants even more detail,
the advisory circular itself, AC 450.1151A, is the ultimate resource. It's all in there.
Good to know.
And, you know, as space activity keeps ramping up, with new rockets, new missions, it leaves you with a question to ponder.
Oh.
How will these already incredibly sophisticated safety analysis methods need to keep evolving? How will they adapt to the new challenges, the new technologies that commercial space will inevitably bring?
It's a great question. It's a field that can't stand still.
Absolutely not. It's constantly learning, constantly improving.
A fascinating thought to end on. Thanks so much for walking us through all that complexity.
My pleasure. And thank you for joining us on FSA Pod. Until next time, stay curious and informed.